Welcome back. We have discussed the types of materials used in construction 3D printing application, mainly cement-based material, but some sustainable options as well. Today we are going to talk about the material behavior when concrete is still wet and just freshly mixed. In conventional concrete construction, freshly mixed concrete is poured into a formwork, guided by gravity and dynamic external pressure from a vibrator to make sure the compaction. Typically, the formwork is designed with greater rigidity compared to the hydraulic static pressure induced by the concrete material. With exceptions like fabric formwork, there is an equilibrium between the stress exerted by the concrete and the formwork, ensuring the concrete remains within the formwork, and that determines the final shape of the end product. Additionally, the formwork shows the early stage of concrete from excessive plastic and dry shrinkage by covering most surfaces during the hardening process. The emerging method of concrete construction, meaning the 3D concrete printing, seeks to depart from conventional formwork-based method and is providing a freedom of shape from pumping and extrusion as they secure their own shape when they're extruded. The departure from traditional formwork methodologies might enhance productivity and potentially save materials by circumventing shape constraints that limit optimal structural design possibilities. The shaping technology involving pumping and extrusion that actually introduced new challenges for the fresh concrete material that result in the specific rheological requirements need to be established to comprehensively or precisely analyze the material behavior. For those less familiar with the rheology, it's a field of physics focusing on the deformation and flow of materials. Covers both solid, liquid, and solid-like materials. It involves parameters such as static and dynamic yield stress, viscosity, strain rate, among others. While some of these might sound familiar from classical mechanics, the plastic behavior is more evident in fresh concrete. The fresh property or rheological property of concrete material is influenced by many parameters like the solid volume fraction, colloidal interactions between cement grains, the viscous dissipation in the interstitial fluid, the thixotropy, and aging over time, and you name it. The fresh concrete can be said dense, non-Newtonian granular suspensions. The yield stress, which is the smallest stress to deform the material or the onset of the flow, ranges a few tens of pascals for self-compacting concrete to several hundreds of pascals for fresh standard concrete, depending on the use of the product. Over several hours, the strength ramps up to some tens of megapascals as the material ages through the cement hydration. And we normally call it as the setting. Printable materials, like any other cementitious materials, behave roughly as viscoplastic Bingham materials. They flow only when submitted to stresses higher than a critical threshold value called yield stress, as discussed before. When they flow, they display a viscous behavior, and yield stress is proportional to the strain rates at a constant gradient called plastic viscosity. However, for most printing processes involve relatively short pumping and deposition phases, meaning the most of the duration of the printing processes are at rest. More than their viscoplastic behavior when flowing, it is therefore the elastoplastic behavior at rest that matters in 3D concrete printing material. Meaning these materials exhibit a roughly elastic behavior below the yield stresses. The thixotropy of these materials and more generally the ability to build up an internal structure at rest is a key feature in most printing applications. When the material is deposited, it exhibits or it shows an initial yield stresses and initial critical shear strain and the initial plastic or elastic shear modulus. With rest, these rheological parameters evolve and experimental results show that the yield stress and the elastic modulus are increasing function of time, while shear strain is decreasing with the time at rest. The material becomes not stronger, meaning higher stresses, but also the more rigid, meaning the higher elastic modulus. From a microstructural perspective, the ability of a standard cementitious concrete or concrete material, cementitious material, to exhibit a yield stress and establish a stable structure at rest, so that actually comes from its capability of form clusters between, or the bond between the cement grains initiate early hydration and pseudo contact points. At the end of the mixing phase, cement particles just like disperse within the liquid medium, resembling a suspension. Due to attractive forces among cement particles, like this, like the interparticle relationship, so they attract and form clusters, creating an interconnected network capable of resisting stress, resulting in an initial yield modulus and yield stresses. So these phases are known as flocculation, governing more physical interactions emerging from the competition between the attractive colloidal forces and viscous dissipation in the water between the cement grains. Flocculation quickly provides yield stress and elastic behavior to the cementitious suspension within seconds after the flow stops. The material continues to reorganize itself for several seconds and ultimately forming the final configuration of interacting cement particles. As cement hydration starts when the chemical reaction kicks in, transforming the soft colloidal interactions into higher energy ridges between the cement particles with the hydrogen bonding, so resulting in an increased macroscopic elastic modulus. So here actually more chemical reaction comes in. Over time, percolated cement particles form parts purely through these hydrate bridges, further enhancing the elastic modulus and yield stresses. These bonds might be like irreversible, but still be susceptible to shear or remixing, but can spontaneously reappear at rest, provided an adequate reservoir of chemical species is available. So during this time, or depending on the time, so some point is the flocculation is governing, and some point is chemical, the hydration is the governing. For printable material, achieving thixotropy is sought after the parameter or the property. Thixotropy involves a time-dependent property characterized by shear thinning and thickening. A thixotropic substance material maintains stability at rest, but can quickly adopt a fluid-like state when agitated. Imagine the printing process again. Initially, after mixing, the materials are placed in a pump hopper, representing a state of rest or flocculation, initial flocculation. So then, as a pump initiates its action via the screw-fed mechanism and pipe, the material undergoes agitation or deflocculation. During this process, some network within the material experiences both reversible and irreversible disruption until the material is extruded onto the surface or onto the floor. Once laid out, the material returns to the resting state, commencing a physical-chemical structural reformation known as reflocculation. The quick strength recovery or strength buildup is a key for a successful continuous layer deposition without failure due to plastic yield and of material at the bottommost. The material's buildup rate typically adheres to the bilinear behavior for printable material, where the faster flocculation rate governs the initial stage because the physical interparticle relationships are governing, while the slower structural duration rate governs the later phase where the chemical reaction kicks in. The terminals of these parameters reflect their roles. Reversible physical flocculation dominates during the flocculation rate phase, while irreversible chemical hydration becomes prominent during the structural rate period. There are frequently used technical terms when it comes to the quality of 3D printed construction material, concrete material: pumpability, shape retention, and buildability. Pumpability refers to the ease of transporting the material from the hopper to the nozzle through the pumping action, or the material's ability to flow smoothly without clogging or segregation. From a pumping perspective, the material yield stress and viscosity shall be as low as possible for better pumpability, where those are normally controlled by water content or chemical additives like superplasticizer. For instance, low water content mixture display high yield stresses and high plastic viscosity. Bad pumpability may cause segregation and discontinuity at the positions. And bad surface quality of printed filaments can be expected. Shape retention or extrudability refers to the material's capability to maintain the intended form or the shape and the structural integrity once it's deposited or extruded. It involves the ability of the freshly printed layers to hold their shape and not deform or slump before they set or harden. It's a competition between the gravitational or self-wear loading and the material's resistance, so the yield stress and thixotropic parameters can be seen as key parameters to control the shape retention. Buildability refers to the ability to develop adequate strength at any given section of a print to overcome the overburden exerting pressure exerted by the subsequent layers without excessive deformation or plastic failure. It is normally characterized by measuring the buildable layer or the maximum buildable layer height without failure. Both material and printing parameters are playing the role for this property, such as yield stress and the build-up rate, thixotropy from the material perspective, pass time, printing speed, layer geometry from the printing parameters. Normally, a high yield stress and highly thixotropic behavior are favorable for better buildability. Good buildability is a key factor to the successful construction of a 3D printed object or structure. It includes the overall feasibility of constructing a design using 3D printing technology, considering aspects such as layer adhesion, structure strength, speed of printing, material properties, and the complexity of the design. Now we can talk about how we actually measure the rheological property of the concrete material. So rheological assessment of concrete materials typically rely on devices like rotational rheometers or rheometry. These tools offer varied measurement techniques, often employing constant shear rate tests to determine static and dynamic yield stresses. Plastic viscosity is measured by multiple yield stress points at various shear rate points, and also a series of measuring constant shear rate tests with different resting period is also helpful to get an insight the material strength evolution in time. However, these tests can be partially destructive and are limited by the device's torque you choose, as the shear rate is strain rate dependent. Additionally, rapid evolution of yield stress may hinder accurate initial measurements due to the sample positioning, and also the sensitivity to the chosen shear rate remains not fully understood. Other researchers have proposed alternative measurement method without rheometers. For instance, the slug test. Gravity-driven techniques offers a simple inline evaluation of yield stress at the printing nozzle level. This method could be valuable in adjusting daily printable material properties for precise geometrical conformity in industrial settings. While it doesn't track material strength evolution over time, the standard deviation seems indicating material homogeneity. Penetration tests, whether it's a fast or slow, present promising potential in qualifying yield stress or evolution and its temporal changes. These tests are keen to rotational flow and set measurements, depending on the probing tool's velocity, an aspect that requires further exploration. Another approach involves the unconfined uniaxial compression test, assessing yield stress and elastic modulus. Because this material, concrete 3D printable material, is highly stiff, so these material is demolded from a cylindrical mold and subjected to uniaxial force to measure its yield stress and elastic modulus. Okay, we've covered a lot today. Now, it might be time for a brain break. So in our next video, we'll delve into additives that manage the flow of 3D printed concrete. Until then, see you later.